Alright, so I did a little more work on this. I feel like having sets as primitive objects is a bad idea. The way this is structured is more primitive stuff is up top, and as we go down we build up, right? Which is why feature is noted before category, where a category is a collection of features. And here, this is where I had set before, but now I've actually moved set down here. So, run through this real quick. A feature is an abstract thing, so it is a schema for a measurable detail of something. So, like a quality or something when you perceive a color or a size or a shape or anything like this, right? That you can detect as different from other sorts of things, right? So this covers a huge range of things, but it's you can discern it from other stuff, and it is not necessarily an entire object unto itself. It is just like a quality of something, right? And a category is a collection of such features. So a category here is still an abstract thing. It doesn't contain members like a set does, right? It's not a collection of objects. It's also not a primitive structure. It's an abstraction layer on top of the. At this point, what I have the most primitive thing. I'm not sure that that's valid. There might be things more primitive than features, but it is an abstraction layer above features. Alright, and then the next one is unit, which I haven't changed much. So this is, we use it in a couple different sort of ways in English, so I just tried to mostly capture that. As a concrete noun, it is an indivisible exemplar of a category. So the category describes the sorts of things, the qualities that something should have. If a unit is something that has those features. So, I feel like that's relatively self-explanatory. It's hard to say when we don't have the vocabulary established yet, but later on it becomes easier to say because you have the vocabulary. So yeah, a unit is something which possesses the features of a category, is a way to say that. And in the abstract, it is sort of a schema of the category's features. So sort of the category and the unit at the abstract level are sort of the same thing. And to identify a unit, you identify if something fits the given category, if it possesses the features prescribed by the schema of the features, and then identify if it is an indivisible example of something that has those, right? So like a field of wheat has the features of wheat, but just as much as a grain of wheat does. But a field of wheat is different from a grain of wheat, right? A grain of wheat is indivisible, and a field of wheat is definitely divisible, right? So that's sort of where this comes in. Okay, now that we have features, categories, and units, we can go on to our most basic mathematical objects. So I don't think here we've gotten into math yet. Here we really haven't either, but this is going to set the stage for the ability to get into mathematics, I think. So 0 is what we're going to call an absence of units. And 1 is what we call the presence of a unit. Right. So if we have identified a unit, then that is 1 unit. Okay? And then a set is a collection of identified units. So a set can have more than one. There is no such thing as an empty set. That is a difference, because an empty set here, it wouldn't make sense. What are you doing? I mean, I guess there is, but like it's kind of fucking useless. And here's my note. If we are working with a category with the features domesticated and canid, then we might name the category dog. And for convenience, the unit of this category would also be named dog for, like, as I mentioned here, the abstract sense of unit. So the unit of the category would be the abstract sense of the unit, is a schema of the category's features. So it will also be the same name because it's effectively the same thing as identifying the category. And thus a collection of dogs would be a set of dogs. Okay? So such a set operates much like it does under a classical set theory, with the notable exceptions that it is not a primitive structure, and no set is infinitely large a priori, as sets are constructed abstraction layers. An infinitely large set must be justifiably constructed to be infinitely large. So there's a few differences here, because unlike set theory, I don't see that it's justifiable to have sets as your primitive object. And I think, like, from looking at the problems that arise, the sorts of paradoxes that arise in set theory, they almost always revolve around problems that would be avoided if we didn't use sets as the primitive object. They seem to almost always spin off from the fact that you're using sets as primitive objects. So you end up with weird problems like, oh, is this set infinitely large or not? Is this set, like, is this an empty set or does it contain anything? Because you don't know anything about it because you didn't build it. It's just something that, like, you have like this Platonist view of it, like it's just there, and then we have to go discern the qualities of it. Like, I think that's stupid. I don't think that's a justifiable way of doing things. Anyway, and then so incrementation and increment, nothing's really changed there. Numbers are about the same, except I did add here. So every practical numbering system necessarily terminates at some point, since new symbols and or rules will always need to be defined in order to keep incrementing. And I mentioned this, I think, in the last video, where, so even if you took the entire planet Earth to write out a number, there comes a point where you cannot write anymore on the Earth. So now you're going to have to, in order to make that number larger, you're going to have a rule of what object in the solar system you move to next to continue writing it out, right? That rule, and no such rule exists in the current numbering system that we use. So our current numbering system actually does have a finite limit of numbers that it can write. So we don't actually have anywhere a numbering system which is capable of describing numbers out to infinity. And it's not even an issue of time or of the size of the universe. It collapses well before that. Yeah. So, thus, if we are to name the set of numbers defined in this manner the natural numbers, it is notably not the case that the set of natural numbers is infinitely large. This is important because this changes the game from set theory, from what we've been doing for the last 130 years or so. This changes it because now, if you want to say that natural numbers there's an infinite number of them, you need to justify that claim. You can't just be like, oh, because of this the successor operator, it just goes forever. You can't say that now, because that's not sufficient. That's demonstrably not sufficient. Because if you can't name your numbers, you're not counting. And if you're not counting, you're not really working with numbers anymore. Right? If all you're doing is incrementing, those aren't numbers. Right? Like the marks on the Ishango bone don't indicate numbers. More likely than not, they probably do not indicate numbers. Because if they had names for those things, there would be abbreviations. There would be a systematized formula for marking off, maybe every 4 or every 5 or every something, so that you can see what it is much more easily. The fact that that doesn't occur on the Ishango bone is a strong indicator that those tally marks are simply tally marks. That is just incrementation, and as such, it is not utilizing numbers. Thus, whatever number of tally marks are on there, it does not indicate a natural number, because a natural number, all natural numbers have names that identify them, and so you can tell it apart from the one before it and the one after it formulaically, without having to count all the way through it or something. Increment all the way through it and compare the size of your two piles of increments. Like, that's the whole reason that we name the numbers. And that naming convention is what gave us the natural numbers. This is completely missed in Peano's formulation of things. And I think it's a really important thing that we shouldn't be missing. And then here's the counting. Yeah, so counting is stepping through the list of number names while incrementing, so it's important that the numbers have names. And then addition I haven't changed, multiplication I haven't changed, I don't think. Exponentiation I haven't changed. Come on, you stupid bastard. Scroll. And then I started adding in the inverse. So decrementation is removing a unit from a unit gathering. And to decrement is to decrease a unit gathering by 1. So actually that would be a set. This, as I'm saying it, I haven't properly come through and changed the names of things. And then subtraction. Down here, I note that it's the inverse of addition. So the addition of a negative is subtraction, or the subtraction of a negative is addition, which are true things. So subtracting is a verb. Simultaneously count to the second number, and starting at first number, decrement with each increment. Okay, so the increment is from 0 to the second number. Yeah, I should probably note that. It's not entirely clear. It does come out here, but I didn't note it correctly. And starting at the first number here, decrement it with each increment here. Okay, so subtraction is the nominal form and the difference is the result of the subtraction. So the difference of 5 and 2 is 3, and we can see that by here we are counting from 0 up to the second number, which is 2. And here we are starting at the first number, 5, and with each increment of this guy, we are decrementing until we reach the second number, and then we stop. And our result is thus obtained, and it is 3. Not necessarily the easiest way, but it's the form of it is pretty much identical to all the others, which is why I've chosen to do it this way, because there's now a symmetry between all of them, and I'm sure that can be improved upon, but this is at least something. And then division works sort of similarly, and taking a logarithm works sort of similarly, except here previously the incrementation stage was always the column on the left. With division and taking a logarithm, it is the column on the right. And I did that because these ones, the result is obtained when the thing that is being decreased hits some trigger value. So for division it's 0, and for logarithms it's 1. So in order to keep the stop and result obtained thing, that arrow the same direction as everything else, I've swapped the columns so that it looks similar. But so yeah, there is a difference occurring in the structure of these, and I think that difference is actually fundamental to why it is difficult for students to grasp division and logarithms when they first encounter them, because it actually is operating slightly differently. The schema that you develop for how addition and multiplication work, and even subtraction really, although subtraction is a little different, but even subtraction, so those three sort of basic classic aspects of arithmetic, the schema that you develop to do them is slightly different than what is required for division and logarithms, and that is actually captured here in some sense. So I think this is actually correct. Like there is a difference occurring in the way division and logarithms occur, are actually executed. So in the basic form, I don't think you can unify the form across all of them perfectly, but this is pretty close. It looks very, very strikingly similar. So I think that is perhaps close to the best you can accomplish. Yeah, but anyway, that's where I'm at. So yeah, I removed set from up here and made it a more derived object. It's no longer anywhere near primitive. So a lot of the paradoxes, like Hilbert-Bernays paradox, don't occur because the reason Hilbert-Bernays occurs is a consequence of sets being primitive objects in set theory, and then you end up with the problem, well, like, what the fuck does the set, what does it refer to? Here, you always know what the set refers to because you defined it. Instead of it being this Platonic object that we're sort of accessing through some sort of interrogation of the supernatural, you know, some bullshit like that. It's something that we build. So you always know at every step exactly what's contained within it because you defined what it is. So you can't end up with a problem like Hilbert-Bernays paradox, because the reason that occurred is there is this weird ambiguity, like, well, am I talking about the entire set, or am I talking about 4, or am I talking about 4 plus 1? And, well, what ends up happening? At the end, we end up getting the consequence that 4 equals 4 plus 1. Because you fucked up, because you used sets as your primitive base unit, base objects that you're operating over, and I think that's the fundamental problem here. So I think this relieves that issue, but I'm definitely going to have to look at it more because, you know, it's only been like 12 hours or something, so, and most of that I was asleep. So I don't for a second think that this is by any means the final form that this is going to take. And I also don't think by any means that I am necessarily going to achieve anything truly novel or useful. But this is where my head's at. So.